let's do some additional steps. We have done this identification with our 3PT1 model, and the result is stored in the file result 8.5.file suffix fz. The question is, what can we do with this digital filter file? Let's try to design a P. So I show you how to do this in Csii. I have opened already this file. You see this is the last element. We throw this away. We have stored it, and I want to show you that we can also load digital filter, an R underline polynomial function. Up R coming from uptast from sampling polynomial function. If you put this block into this window, then the program can be filled with polynomial function of z to the power of -1, discrete time function. And here we can load load an FFZ file. The help text was not compiled into English. I've seen just now. Okay, you see, okay, these numbers maybe you have not in mind. The sampling time was 19 milliseconds. Maybe you can remember this value. So this is the result of the identification from the RLS Offline method. We say okay. So now this is a digital filter which can be used for a design of a PIDT1. So we put our controller, say OK, add the elements to close the loop like before. So close the loop with branches and add a minus sign. Go to controller design, say OK. Yes, we want to have a D part. We stay with 5. We take the proposal, say OK, take the proposal for the program. We cannot do anything else because we don't know any time constant of this block, so we have to go with the -12 dB method, say PIDT1. In the Bode plot design here you see the phase curve has some strange behavior that comes from the digital filter window. Doesn't matter. If we close this box, we see a gain here and 2 time constants here. So the resulting controller of this digital filter can be written now on our paper to have some resulting nodes. Design this controller, and the result is okay, I think the battery is low. Okay, so I now can note the values. Csii is 0.4154. Tn is 1.4723. Is 0.8422. If we want to check if this controller works properly, then we have to combine this controller with our original 3PT1 process. Again, always the same. So this controller carries this number 4154. Is that right? Check 4154. Okay, this is a controller with 41454, which should be stored in our register. Store, close, okay. And now we throw this away. Whoops. Load the original process. the loop was 3PT1, open. This controller was the original one. I want to show you a redesign. I have done this design some hours before, but I think I should repeat this because you should see what happens with our numbers. If I have the manual typed in second largest process time constant, and I get the largest time constant for the PI part with our values, then I get a controller with a gain 0.39, and the reference step response, we will see this. I delete all curves and recalculate the reference step response for this controller. It's this curve. We have stored this curve, doesn't matter, but I want to show you. I store this curve now, close this box, and make a redesign of the original 3PT1 process with one difference. Now I accept the proposals derived with the -3 dB over a decade method. Say OK. Again, derive. I take the proposal into this field. This gives a small difference in the controller box. I show you the resulting value here. The K is a little bit larger. You see, the time constants are different, and if I calculate this step response, then we get this curve. So, blue curve with manual typed in time constants, red curve with the proposals of the curve. I store this curve, and now note what happens if I go with the right mouse button into this field, open the PIDT1 converter, and now I recall the controller which I have derived with my 8.5 method RLS Offline. I click on this, say copy, again note 4145, copy, OK, and now look what happens. The next curve is green, and if I recalc, then you see this is absolutely identical to the original design. So the digital filter behaves absolutely very near to the original 3PT1 process, in spite of the fact that we cannot compare numbers. Okay, you see, this identification gives good results with our 3PT1 system. We can do one. No, I think that's all what we do with this 3PT1 model. We close this 3PT1 model now because we want to go to the next point. But before we leave this point, I want to show you in my paper, in the previous pages, another example or two other examples. I don't want to do it live in my video, but want to show you this. Also dealing with this RLS Offline identification method. This is the same what we have done, but now you see I have changed now the signals. What is a blue signal? The blue signal was the response, the output of a PIDT1 controller used in my 3PT1 system, and then the green curve here is the red curve is the response of my closed loop system working with this PIDT1 signal. So I change the input signal to the blue curve, get a new output signal, and the resulting parameters are very near to this. Let's look for this A1 value. A1 is -2.92. -2.92. So independent of the signals, the resulting A's and B's are the same. Here, this is a comparison of Bode plots. I think that doesn't matter, but what I have done in the next example is the following. I have invented a digital filter model. with B1, B2, A1, A2. Then I invent an input signal. The input signal here has some pulse values, 1, 02, negative 04, 1, negative 04, and so on. This is a signal, yeah, like the blue curve here. Then I calculate with this input signal and this filter the output signal. That can be done with WinDF C#. Then I store the input value as file. I store the output response as file. Load both files with my identification box. And yeah, I just have used 4 points. 1, 2, 3, 4, 5, 6 points. Sorry, 6 points for the identification. And the result is after identification. The result here, you can see the resulting point. A is 0.2, A1 is negative 0.2, A2 is negative 0.3, B0 is 0, 0.4, 0.5. So you get exact, with this identification, exact the same model. And a last example is using my adaptive advanced controller box. There you can also create some input and output signals. You have to activate this checkbox to store also the output of the controller. XR here is the name for the output of the controller. If you do this and run your system, store the signals and identify this used process model, then you get the same good data. Yeah, so I think this is enough for this method 8.5, so that we can spend some minutes on the last identification method I want to present in the chapter 8, and then I leave this chapter to show you one very, for me, very impressive method. Also, this method is more than 30 years old, developed in a digital filter book from Mr. I give you the link to the copy of the book pages for this recursive algorithm. The idea is the following. I sketched this idea also in my paper. Wait a moment. Now, I give you some information. 8 point online identification. The name of the method is recursive least square identification. I give you some more information for this, but first the main principle. The main principle is the following. I have a running loop controller C together with my process FP. The X value, this is the Y value, the output goes back to the input. Here I have the desired value W. So this loop runs continuously in a digital system. So this is a digital controller, that is a FC, is a digital process, in analog process, but with a digital transfer function. Okay, during runtime, the method samples continuously the input of the process and the output of the process. So here you get values yn, xn. With this information, and you get in time, get you a new information, new point new point X and new point Y. This is the 8.6 identification. You get process model, a new actualized model FFC. The system runs without any interruption. You control your output to the desired value W, and if there are and in each sampling new controller output value, which is the input for your process, and the new output of the process xn, and these both informations are loaded into my online identification, and in each new sampling time you get new parameter set A's and B's of a process model. Okay, we can see this model, and what we can do is in my simulation I change the parameter here, and then you can see how fast the model follows this change. And then we can do more. We can now take the new identified models and make a design. Each sampling time make a new, which throws out a new FFC controller, and this controller then is copied into the loop. This is called online adaptive system. Adaptive. That means if there is a change or not of signals, if the change of model parameters, say the K goes up and down, or the time constants of my process goes up and down or changes, then automatically these changes are sampled, used for a new identification, for an actualization of the process model. Then this new process gives, with the design method, a new controller, and this controller then is sent to the closed loop system, and automatically in each new step you will have a new controller which can now work better to your change process than your old controller. That is a since, in spite of 30 years old mathematical theory, today a very modern system, because this leads to a system where you need not to design a controller. The machine does a job for you. That is a so-called adaptive system, where the controller automatically is calculated by your system. This, of course, works only if there is a change of signals. If we have a steady state situation where there is no change of the signal, so here's a DC signal and here's a DC signal, of course then the identification must fail, because then we have only information about the DC values and not for high frequency values. That is a then this system cannot design a controller only with the DC gain. You can imagine that this is true. So in my simulation I show you a system which has a desired value which goes up and down, say each second. So this is a rectangular signal, and this should follow as fast as possible, and then in my simulation I can change these parameters, and then you will see this automatically changes the model parameters and the controller parameters, and automatically the control loop is adapted to this change. So the depending on the controller type, you see this is chapter 9. We have not talked about controllers which can be designed with the knowledge of an FFC. This comes in chapter 9, where I will present some controller design methods which can be done in 1 millisecond. If you imagine the design of an FFC we have done with Csii. Csii calculates the Bode plot of a digital filter which takes several milliseconds. then make the FRA design, which also takes several milliseconds. And the controller comes then after 10-20 milliseconds out of my design. This is not suitable to do in an online adaptive system, because here you have to be very fast, and I show you in chapter 9 some digital controllers which can be designed very fast in microseconds. Yeah. Before I start the simulation in the next video, I want to give you some more information about the mathematical structure behind this method. I have opened the folder docs, which was still hidden up to this point, in your Lernraum course, and here you can find some documents which of course only be usable during your study. Yeah, please don't use these copies of literatures after your study. Yeah, you have to delete them. And I close this folder just, I think, end of this week. But I think that is important to know that in the first document here with leading number 8.6, it's a chapter number, and all these are chapter numbers of my document. This is some pages of the book which describes exactly this recursive least square method from Mr. Isermann. Isermann was a German professor at a university, and this 30 years old book contains the background. I use this book and convert the mathematical background into an algorithm, and you can have the source code of this algorithm. In my paper, I have a very compact description of this method. You can find the mathematical description here, the theory, in this paper. Important is that we want to have a new set of parameters. The theta, you can remember from the previous identification, the theta contains the a's and b's of my model. This is theta plus 1, then it's theta. So you can imagine that 1 point with a y and the x value is not enough to identify, say, a second order system. So this is an iterative method. Iterative means you need some steps to have a good model. And this is an update of the a's and b's in each step. This is the old set from the previous step. And if you look here into this algorithm, then you see the new parameters can be calculated out of the old parameters. That is a recursive version. You need starting values to get new values with this equation. And this equation contains the new output value, contains a correction vector, and here again this are the a's and b's, and C is the matrix filled with old input and output values. Note that there is no inversion. No inversion means that you have not a numerical heavy load of the microprocessor or of the computer. This method avoids inversion of your solution of the equations. You need just filling of a matrix and a multiplication of one matrix with another. So this is compact described in this element, and here you can see I have in my source code some functions which do the job here. And if you want to copy this source code into another computer system, just look on these equations and look on my source code, and then you find all things together. The best way is to demonstrate this adaptive mechanism in the next video, so that you can see, okay, this is a really good idea which works very, very good. For this I start WinDF C#. This contains this method, but what you must know is that in this demonstration I of course need some controller types which are still not described, coming in chapter 9, but I think this is a good way to go into chapter 9 to motivate you to follow me with my modern control systems, because you should know the method describes an identification method throwing out an FFZ, and now at this time you don't know any controller type which can be designed with FFZ in a fast way to get a digital controller parameters. So this comes later, but I show you 2 of these controllers running with my closed loop system. So what you will see is the following. I start hardware simulation of my process, second order system. I design some starting controllers. I run the loop not only with a step response, but with a response on a rectangular desired value. The desired value jumps up and down. The output try to follow this up and downs. And what I can do in this demonstration, the next video, is then I change the K's and T's of my process, and you can see then what happens with the closed loop system, if there is an adaptation or not. Yeah, so it's rather complicated. The most complicated demonstration what I can offer, and in the lab, hopefully we will have a lab. You also should play with this design methods to be a little bit more familiar and to see what is possible in modern digital systems.